Hi, and welcome to my talk, a review of modern code Deobfuscation techniques. My name is Arnau Gamez Montolio. I am graduated in Maths and Computer Engineering. I'm also the president of Hacking Libre, a non-profit organization around ethical hacking and social aspects of it. I'm also an organizer for the R2 Congress, the Congress about the reverse engineering framework, rather to. First of all, a bit of a warning. This presentation may contain traces of assembly and also a little bit of formal maths, although it won't be required for you to follow those more formal aspects, as I will explain them very, very straightforward for everyone to understand and to get it. So the contents of the talk will be, first of all, introducing what is code deobfuscation and some basic techniques that we usually encounter. Then I will present you a brief theoretical-ish approach to mixed boolean arithmetic expressions and how can we use them in order to obfuscate mathematical expressions and at the end arbitrary code. Then I will present you what is program synthesis and how can we leverage this technique or these approaches in order to deobfuscate code, some existing work and recent research in this area. And finally, I will show you R2Cynthia, which is a tool I developed that integrates a program synthesis tool known as Cynthia into the framework and the reversing framework R2. And we'll see a little bit of some demos. Finally, just showing you the conclusion, some feature work, and a bit of references in case you're interested, just to be able to follow with the topic. So let's begin. When we talk about code deobfuscation, we have to place the context in the area of technical protections against the mate attacks, which are those attacks where the attacker or the analyst has a complete instance of the program and controls the environment where it is executed. As you can see in this diagram, obfuscation lays below the technical aspect of the protections, where we also have legal protections as well. So what is code obfuscation? In a nutshell, we call code obfuscation a transformation from a program, an input program P, into another program P prime, which is functionally equivalent, but which is harder to analyze and harder to extract information than from the original program P. Who uses code obfuscation? So I differentiate basically to different actors. And first of all, related to software protection, and then also for malware, it's used in malware threats. And why? So the main reason is just to prevent, although in reality it's usually just complicating the process of reverse engineering. In the case of software protection, this is motivated due to intellectual property and digital rights management. And in the case of malware threats, we have an intention of avoiding automatic signature detection, and also if slowing down the analysis, which leads to more time uncovered and more money, usually, that malware actors are able to generate from that. And how is basically applied those transformations? So usually the idea is to mess, to complicate the program's control flow and the data flow. Different abstraction levels, we can see source code, a compiled binary, or even an intermediate representation, and those transformations affecting different target units. We can have, for example, the whole program, a function, a basic block, or even a single instruction. Just as a side note, a remark that many weak techniques that we can encounter that from them used alone could be not as hard to break, but usually we can combine a lot of them arbitrarily to create hard obfuscation transformations. So here we have a table from one of the references I will give you afterwards that presents basically most of the known obfuscation transformations to today. So I will start presenting you a few examples. Let's start with control flow obfuscation techniques. The first one would be opaque predicates, which are very classic obfuscation transformation. An opaque predicate is basically a specially crafted Boolean expression, P, a predicate P, that always evaluates to either true or false. That is, at obfuscation time, the one who is doing the obfuscation, the transformation of obfuscation, knows the value of P, and it knows to be always true or false. That way, we can get some snippet of code and just branch it into two different paths, one of which will be the rest of code, the valid code that will always be taken, and the other one will be just junk code that will never be taken. This path will never be taken. Another usual technique for control flow obfuscation we find would be the control flow flattening, in which we basically change the structure of the function's control flow graph, and we replace all the control structures with a central and unique dispatcher. You have to think of a massive switch statement. In this case, we have this code with its corresponding control flow graph. As you can see, you observe that the green arrows point to the nodes that represent the branches that will be taken when the conditions are evaluated to true, and we have this control flow graph. So if we flatten this control flow, we will get something like that, in which we introduce a new variable, which will be, in this case, the next, that will be used for the switch, and each case for the switch will get us to a different place of the code. Okay, so at every time we go to one of the nodes that represent one case of the switch, we get back to the switch and go to the next one, depending on the result put in the next variable in each of these. Let's see a bit of data flow obfuscation techniques. First case, here I have dead code insertion, where this is a technique where we deliberately insert instructions into our code that do not have any effect in the computation's outcome. As you can see in this, both in those snippets, in the C snippet and the assembly snippet, the remark instructions, in this case x equals 1 and z equals 3, and also in the assembly listing, the move EAX1 and move ECX3 that are marked, those instructions do not have any effect in the outcome of the computation. So we call this dead code insertion, because basically this code that it's dead is useless. We can also find another data flow obfuscation technique known as encodings, which they are used to prevent a specific value to appear in clear at any given point of the program execution. And the basic idea is we can compose a pair of functions, f and g, for example, in which when we want to apply an encoding function, this will be the case when we are interested in hiding this value. So here we see that instructions sub EAX x1, 2, 3, 4. We apply the f function, which will be the encoding function. We push that value to the stack. We do whatever we need with them. And when we need to retrieve that value, the original value, we just have to apply the decoding function, in this case g, and this instruction remarked in the assembly listing in blue. Finally, for data flow obfuscation techniques, I will present you pattern substitution, which is a technique in which we can transform one or more adjacent instructions into a new sequence of instructions that is more complicated, usually involving more instructions, but it preserves the semantic behavior, which means the outcome is essentially the same. In this case, we have in the first two columns of the assembly listing, we see that the blue marked instructions are semantically equivalent. We have used just a pattern substitution in this case. And then the first instruction of the second column has also been substituted with another 4 instructions in the third column, as you can see, both marked in blue, which are, again, more complicated new sequence of instruction that preserves the semantic behavior of the original one. So, as you might expect, this process can be used iteratively until any number of iterations that the person or doing the obfuscation would like. So with that in mind, with that context about code obfuscation, we would like to define code deobfuscation as the transformation process that gets as input an obfuscated program P prime or a piece of that program P prime, and converts it into another program, another piece of program P double prime, which will be easier to analyze and easier to extract information than from P prime, which is the obfuscated part. However, although ideally we would like that P double prime is basically similar, equalish to the P, the original program P, which has been used for the obfuscation, this is very, very difficult to guarantee. In first place, because the analyst or the attacker does not have access to the original program P to compare. Otherwise, it would be a waste of time trying to deobfuscate if you have access to the non-obfuscated version of the program you're analyzing. Then, also, the point is that usually the analyst or the attacker is only interested in some specific parts of the program being analyzed rather than the whole program, and it's usually interested not in reconstructing a functional program, but more on understanding what is doing on some part of it. So usually we don't need to reconstruct a valid program when we are dealing with obfuscation. We just want to know what's going on in there. So let's see a bit of what are mixed Boolean arithmetic expressions and how can we use them for code obfuscation and why are they important. Let's define them informally as an expression, a mixed Boolean arithmetic expression would be a mathematical expression that is composed of mixing of operators among the integer arithmetic operators and also bitwise operators, as you can see here. If you want to get a little bit more formal, you could get this definition we have here in pretty LaTeX form. I won't go over it, but I just wanted to leave it here in case you are getting mathier and want to get a little bit more formal definition, which encompasses what we just said in a formal way of a mixing of operators in the expression. So you can see here just in bold we have differentiated what are polynomial mixed Boolean arithmetic expressions and linear mixed Boolean arithmetic expressions. These won't be really important for this talk, but if you want to get a little bit into the theory of that, it's quite interesting the difference and what kind of things can we do with such restrictions as linears, for example. We have more tools to deal with them. But anyway, this is just for the people more interested in going to it more formally or studying the mixed Boolean arithmetic expressions from a theoretical standpoint, which I will give you references to that if you're interested. So here you have a couple of examples. It's for polynomial expression and a linear one. And essentially, as you can see here, they are just expressions that mix operators from bitwise or Boolean world and the arithmetic of integers world. So how can we obfuscate with that? First of all, let's take into account that mixed Boolean arithmetic expressions are provides us a mathematical background to deal with the kinds of expressions we could obtain from a set of instructions for any computer architecture. So when we talk about obfuscating with this kind of expressions, we are talking of essentially being able to perform obfuscation in the terms of instruction, actual computer instructions. So with that in mind, let's talk a bit of what we call MBA rewriting, which is essentially getting an operator and rewrite it in an equivalent expressions, but more complicated. Let's say just rewrite and give an operator with another expression that is equivalent to the initial one, but it's more complicated. Okay, and the outcome of this process generates what we call the rewriting rules, and we have some of them in different references, and we have also some methods to generate them. I won't go really deep into that, but I will leave you the references if you're interested in that. Then another common technique for obfuscating with mixed Boolean arithmetic expressions would be what is known as the insertion of identities, when we just compose two different functions that are inverse, modulus some number of bytes, essentially modulus 2 to the n, where n is usually 8, 16, 32, or 64. And for understanding better that both the MBA rewriting and insertion of identities, let's see just an example to obfuscate a very, very simple expression. So consider the expression x plus y and the following functions f and f minus 1, which are inverse, working on 8 bits. So first of all, if you apply the rewriting rule that we have seen just before to the original expression, we would get this one, the e minus sub 1 expression. Remember, we are just using this rewriting rule. Then we can use the insertion of identities that is produced by those functions that we have just defined. First of all, we apply f to the expressions that we obtain from the rewriting rule, and then we apply f minus 1 to such expression obtained before. So we just get the final expression, which is this one that we see here, expanded. And as you can see, it is far more complicated than the original one that was only x plus y. So we have essentially obfuscated our expression. How can we deal with measuring the complexity of such an obfuscation transformation, or more general, the complexity of a mixed Boolean arithmetic expression? So essentially, we can represent such expressions are directed acyclic graphs, which will identify commons of expressions. That is why we consider that if an expression has commons of expressions, this does not increase the complexity of the overall expression. So based on that, we find a few metrics that can give us some idea of the complexity of such an expression. First of all is the number of nodes of this graph representation. Then the MBA alternation, that is basically the number of times we change the type of operator we have in the expression from integral arithmetics to Boolean ones, and also the average bit vector size of each operator and operand, which is basically the bit vector size in which it is operating. So what are the theoretical simplification approaches that we can take in order to basically simplify such expressions, such mixed Boolean arithmetic expressions? And in the first place, we find what we call the bit blasting approach, which the basic idea is to find a canonical, that is a unique representation for such MBA expressions. The idea is representing the MBA expressions as Boolean expressions that are obtained by computing the effect of each operation on each bit of the resulting value. So we are getting Boolean expressions for each bit of the resulting value. We leverage for that the algebraic normal form that guarantees unicity, which is basically we express all the Boolean expressions we get will contain only XOR and AND operators. And the advantages that this approach has are basically that we are transforming the problem of the MBA simplification into the problem of simply Boolean expression simplification. Although we find a few drawbacks as well. And in the first place, we have that the process of canonicalization can be very, very expensive, both in memory and in time. And also identifying the word level expressions once we get Boolean expressions on each bit of the resulting value is far, far from trivial. There is still a ton of work to do, theoretically talking, in that aspect. And finally, we find that it's really, really hard to scale for this approach when we get to a larger number of bits. Think of anything that is bigger than 8 bits will be extremely hard to deal with that. Then we find another usually simplification approach that is usually taken, which will be what we call the symbolic approach, with the idea being just finding an equivalent expression, but in a simpler form. Basically, we want to use the existing techniques for simplification that we know for arithmetic simplification and for boolean simplification for those parts of the expression that contain only one type of operator. And then we can use a term rewriting approach to create the missing link between those sub-expressions that alternate different types of operators. The basic idea is that we can generate rewriting rules for the obfuscation the same way we did for the rewriting rules used for obfuscation, just inverting the direction of the ruling. As you can see here in this example, we just inverted the direction of the rewriting rule we used before for obfuscation, and we just get a rule for the obfuscation. The main advantages that this approach presents is that the simplification is not impeded by an increasing number of bytes. We are working on the word level, and also the representation of the expressions is far, far smaller than the representation in a bit blasting approach. Although we also find some drawbacks. In the first place, this approach is very sensitive to the size of the obfuscated expression, the total size and number of nodes in the graph representation, if you want to think that way. And it's also highly dependent on the chosen set of rewriting rules for the obfuscation. If we lack a rule that will be used for the deobfuscation, that its inverse was used for obfuscation, we won't be able to go as far as if we had that rule. So it's really, really dependent on the set of rewriting rules for the obfuscation that we have for this approach. So let's go now right into the program synthesis part, and I will start with a motivating example. So consider the following function, which represents an obfuscated MBA expression, and we are interested in its behavior. So we are just going to treat that function as a black box, throw some inputs, and observe the output. Let's just observe how it behaves, but without paying attention to the internal details that define it, okay? So we treat it as a black box, we throw some inputs, we'll get the outputs. This is shown here. So essentially, in program synthesis, we are interested in learning or synthesizing a simpler function that exposes the same input-output behavior. In this case, such a function would be this one, h, which is just the sum of the three input values. In order to define program synthesis, we could say, a little bit informally, but it will be enough for now. It's just the process of constructing programs in an automatic manner that satisfy a given specification. And when we talk about the specification, what we mean is we want somehow telling the computer what to do, but letting the implementation details to be carried by the synthesizer. Okay. What kinds of specifications can we find for such approaches? In the first place, we can find formal specification approaches, which will be just specifying the behavior of the program in some logic, for example, in first order logic. In this case, we just have here define a program that for any input on 64-bit values, we just add 7 to that input. Then we can also define a specification as a set of input-output pairs that just describe the program behavior, as we have seen before. In this case, we just have the set of pairs. And another way of specifying or giving a specification is having a reference implementation that we call an oracle. Even if that seems quite strange, this will let us to generate pairs of input-outputs that describe exactly the behavior that we want to synthesize. So essentially, our approach for our problem, that is basically called deobfuscation, its nature leads to a kind of inductive and oracle-guided program synthesis style, which uses the obfuscated code that we have as an input-output oracle. That essentially means that we will want to generate a set of input-output pairs from the obfuscated code, the oracle, and then determine the best candidate program that matches the observed input-output behavior. So, some practical considerations before going on. When we talk about constructing candidate programs, what we are essentially doing in real world is we are defining a context-free grammar that will encompass all the primitive components, the terminals that will be essentially be which variables are we using to create our expressions, and also the ways in which we combine them, the production rules of the context-free grammar. Then we usually need to set some boundaries that will delimit the task of program synthesis, let it be the number of input-output pairs, the number of terminals and derivations of the context-free grammar to construct the candidate programs, and we would need to ensure that that task of program synthesis terminates. So basically, we need to put a maximum number of iterations or a timeout for each task. And finally, we usually need to decide when we consider that a synthesized candidate is valid enough, okay? And whether we want to introduce some kind of equivalence checking and in which way. So what is the existing work in this kind of program synthesis approaches towards code deobfuscation? And in the first place, I would like to mention Cynthia, which is from 2017, that uses a stochastic Monte Carlo tree search-based stochastic program synthesis approach, in which essentially we convert the problem of finding a candidate program into a stochastic optimization problem. That essentially means that we are generating intermediate results at each iterations that will evolve towards a global optima that will be our best candidate program, and this evolution will be guided by a cost function that will just compute the somehow similarity between what the code we are trying to synthesize and how it's behaving, and the behavior that we are getting by those intermediate results. We'll see a little bit of that afterwards. So we are really lucky that we have a public and open source implementation of Cynthia, and this indeed will be some of the basis for our work on R2 Cynthia, as you might have guessed already. We will talk a bit more about it in a second when we present R2 Cynthia. Another really interesting work that came up just a few months ago is what's called QSynth, which is the title of a paper presented a few months ago, as I said. And it presents an offline enumerative program synthesis approach for also towards code deobfuscation and treating mixed boolean arithmetic expressions as well. And the basic idea is having a context-free grammar, we want to generate all the programs up to a certain number of derivation of that grammars, and then we just create offline lookup tables that map each candidate program into its input-output behavior given some set of inputs. And just we perform an exhaustive search for the candidate programs, the mapping of candidate programs with each behavior, to find which one presents the same input-output behavior as the oracle we used to generate the input-output pairs, that is essentially the obfuscated code. In my opinion, the most significant contribution of this work is not, even if it's interesting that they use that approach of not using an stochastic approach, but an offline enumerative one. My opinion, the most significant contribution is that they presented an algorithm, a process that lets to split an obfuscated expression into smaller sub-expressions, then being able to synthesize those sub-expressions individually and finally reconstructing the total simplified expression. So this opens the door for a really scaling the process of synthesis, even if we want to use some other approach, not necessarily offline enumerative. But the idea and the process that they present for splitting the obfuscated expression into smaller sub-expressions that can be synthesized by their own, and being able to reconstruct the total simplified expression, this, in my opinion, the most interesting contribution that they did. So the bad news is that we have no public implementation available, and I don't expect that they release any of that, because in their paper they already say that it's integrated in some internal tool. So let's see what goes on in this direction, but certainly I'm pretty sure that there will be people, and I will try myself as well, to implement something that integrates that idea of splitting the obfuscated expressions into smaller ones. So let's see how this goes on. What are the limitations of those approaches of program synthesis, especially Oracle-guided approaches that we have seen? First of all, dealing with code or expressions that are on their own very complex semantically speaking. So think of cryptographic expressions. We want to derive cryptographic primitives, for example. If we want to derive a program or an expression that gives us the behavior of an already complex expression, just from its input-output behavior, this will be extremely difficult, because we won't be synthesizing something simple, but something that is already complex semantically speaking. Then, of course, dealing with some source of non-determinism in the code will be basically impossible to synthesize such a thing, because if we are relying on the input-output behavior, but we cannot actually rely on it because it has some non-determinism inside, it will be really complicated to synthesize such programs, such code. And finally, what we call the point functions, which are those functions that they give us the same output value for all inputs except one specific input that gives a different output. So if we try to synthesize such expressions just from randomly sampling the input space, it will be actually very difficult to get anything meaningful. So now we'll present you R2Cynthia, which is the tool I have developed. And it's essentially based on the following component. First part, Radar2, which is the fully fledged reverse engineering framework. Then Isil, which is the Radar2 emulation engine, which is integrated. And also Cynthia, which is, as you might have guessed, a program synthesis-based framework for Deobfuscation that will be synthesizing the behavior of the obfuscated code given its input-output behavior, observable behavior. The basic integration of that will be that from an active R2 shell, where we are performing some analysis of binary that contains obfuscated code, we just call R2Cynthia script, okay? So then from R2Cynthia, we will leverage Isil, communicating with the R2 shell, to generate the pairs of input-output values for the specified variables that will be essentially the registers and memory locations that we are using for input and output. Once we have that, we just invoke Cynthia from R2Cynthia with the generated input-output pairs and also some configuration variables. And essentially, the result of that will be that we will be able to synthesize the code semantics of the output variable, that is a register or memory location, with respect to the input variables, again, registers or memory locations. So let's just go into a guided example that will serve as an illustration of the process and what are we actually talking about. We start with some piece of non-obfuscated C code. In this case, we have the function ef49a, which essentially the only thing that it does is returns the value obtained by multiplying the second parameter times the fourth parameter. And then the target function, which the only thing that it does is calling the previous function. We will see in a second why we have such a construct. So when we have that, we want to obfuscate the functions. In this case, we use the Tigres version 2.2, which is an academic obfuscator, using the following techniques. In the first place, encode arithmetic, which will replace the original expression with an equivalent and more complicated mixed boolean arithmetic expression. And then we will use encode data, which essentially will encode the integer arguments before calling the function, decoding them at return, which is using the encodings technique that we have seen before. So now we have this phase from the non-obfuscated C into obfuscated C using Tigres, and the code looks like that. This is the f function where we just replace the multiplication of the second parameter and the fourth parameter with this large mixed Boolean arithmetic expression that is equivalent. And also for the target one, what we are doing is essentially encoding the parameters before calling the actual function. That this will be decoded at return value when we return from this function. Okay. So once we have that, we just compile that C code and we obtain an obfuscated assembly counterpart. So let's explore a little bit of such an assembly. So I'm opening the obfuscated file. I will analyze code to obtain flags for the functions. And if we just print this assembly of the function target for an 8, okay, here you see this function. This is the C function target that we have seen, getting those values as the inputs, and then essentially this encoding with the values we have seen, all the inputs, and once the inputs are encoded, it's just the only thing that it does is calling the function f that we have just seen. So let's now take a look at this function. And this assembly listing that I'm not expecting you to read, but I only want to show you how long is it with respect to the target. For example, it essentially contains just the multiplication between the second and fourth parameter, but obfuscated. So it is code that computes multiplication between second parameter and fourth parameter, but obfuscated in the way that we have seen in the C code. So basically, this is all the obfuscated assembly instructions that perform such an operation. Okay. So if we want to address the task of deobfuscating such code through, for example, a symbolic execution approach, what we will obtain would be an expression that represents the return value, in this case, what will be in the register EAX at the end of this snippet of code, the call to target function. So we would obtain an expression for such a value with respect to the input variable, okay? The input variables in this case are the 5 first registers for the calling convention on 64 bits. Sorry, I said output value will be EX. In this case will be RAX because we are in 64 bits, but anyway. So let's observe the resulting obfuscated MBA expressions that we obtain if we run a symbolic execution engine through this obfuscated code in order to get the expression for the return value with respect to the input variables. So essentially, this is the way that looks such an expression. So here we have RSI and RCX as variables, which are the second and fourth inputs, and this is essentially the expression that gives us the result that will be in the RAX register after we call the function, essentially its return value. So as you can see from here, the syntactic complexity of this expression makes it totally unapproachable and I would say useless for us to derive any understanding from it. So basically we have obtained an expression for a return value that is useless because it's too complex on the syntactic level. But remember that its semantic behavior, its semantic complexity, if you want, is, I would say, trivial. It's just multiplying second input times 4 input. So we will leverage R2Cynthia to just extract the actual code semantics. We will synthesize the code semantics just based on the input-output behavior and not being limited by the syntactic complexity of the expression itself, of the instructions that are defining this obfuscated code. So let's take a look at that. Let's print this assembly of the function target again, which will give us the boundaries of the obfuscated code. In this case, we will start just in this instruction, and then we will end at the end of the function, which will include all the call to the function f that we have seen before. So let's take a look at that here. So here, as you can see, we are calling R2Cynthia. We first of all indicate the bit size we are working with, then the initial offset, the starting offset for the obfuscated code in the file we are analyzing. As you can see, this is essentially the offset where the target function begins, then the finish offset, which is essentially the last offset of the memory direction where the last instruction of the function is, and then we pass as input variables those registers, which are essentially the registers for the inputs, and finally we pass the output variable that will contain the output of the operations. So if we run that, it will output a lot of verbose information that I put out for you, and I will go over it a little bit. So here we have, let's let it finish and then we will comment about it. Okay, that's it. Let's comment a bit about it. So essentially, first of all, it just prints the information that we pass to it, the bit size, the start offset, the finish offset, the inputs variables, and the output. Then what we do is we are generating the input-output pairs, and essentially we are using ESIL, the emulation with ESIL, to give values to the input variables, in this case, those registers. So basically, those values that you see here in the input-output pairs are hard-coded to the registers at each pass of the emulation. So we just give those values to the input registers. We emulate all the code until the finish address, and we observe what value lays in the output variable, which in this case the RAX register. We do that a bunch of times, and we collect those pairs of inputs and output. Then once we have that, we can create the context-free grammar that we will use, that Cynthia will use in this case, to generate the candidate programs. So essentially, we start with a non-terminal variable that we call just U64, and we have the following terminals for the grammar. We have all the input variables, in this case the registers, and also those operators. So essentially, with that, we can apply those different production rules iteratively. Here you have in reverse police notation, which is actually how it is implemented internally, but here you have the nfix representation just to take a look at it, a few more readable. Okay. And finally, we just said that the starting variable for the context-free grammar will be the only non-terminal that we have. So applying those derivation rules, we can generate candidate programs, candidate expressions to meet the input-output behavior that we have observed. So essentially, we just now call Cynthia from R to Cynthia, and it starts doing some iterations of the Monte Carlo tree search, generating intermediate candidate programs until we find a reward of 1, in which case we will obtain essentially an expression that gives us exactly the same semantic behavior. And as you can see here, the final expression found with reward 1 is essentially RCX times RSI, which is, as we know, second parameter times fourth parameter, which is essentially the semantic behavior of the code that we had initially, that we obfuscated at the C level, then we compiled to get an obfuscated assembly counterpart. And as we have seen before, if we extract its expression with a symbolic execution engine, we obtain a massive expression that is useless for us because we cannot derive any information from it. But if we synthesize its behavior, just observing its input and output, we can call Cynthia in this case to learn a function to construct a candidate program that matches this behavior, this input-output behavior. In this case, as you have seen, in less than half a second, we obtain essentially the semantics of the obfuscated code. So basically, that's it. And if you're wondering when will be this published, it's already published. So you can go play with it to that GitHub repository. Please note that it's on early stage and it's on alpha stage, I would say, but it works, and you can use as variables for inputs and for output both registers and memory locations. You have some examples in there. I'm planning to extend it, or maybe to transform it into a native Radar2 plugin that will give us some more space for configurations and other stuff that will be much easier to handle than just having a single script file. But anyways, you can already go there and play with it and report issues, bugs, or whatever. Extend it for anything you would like with it. It's there for you. So let's see a bit of the conclusions of the talk and my work in here. First of all, a few takeaways. Mixed Boolean arithmetic expressions can be leveraged to obfuscate data flow of a program. This has been demonstrated before. We can use MBA rewritings and insertion of identities, and we've seen, for example, Tigres that is using the encode arithmetic transformation that essentially does a replacement of an expression with a more complicated mixed Boolean arithmetic expression. Also, that current deobfuscation techniques that are mainly based on symbolic execution and some variations, even if they are super useful for a ton of cases, when they address simplification of this kind of data flow obfuscation, usually they're very limited because they're strongly tied to the syntactic complexity of the code that they are analyzing. So this gives some limitations, some clear limitations to those approaches alone by themselves. And finally, we have that there exists, and we already have some implementations of program synthesis approaches that are quite novel, that allows us to reason about the semantics of the obfuscated code and being limited only by its semantic complexity, but not for the syntax complexity. For future work, I would say that there is a ton of work to be done on the theoretical aspect of mixed Boolean arithmetic expressions treatment. There is really a lot of work to be done here yet, and more mature theoretical development can lead to better approaches for simplification, both on a theoretical aspect and also to improve even more some techniques, for example, from program synthesis or other approaches that we could take. And from a more practical standpoint and more immediate, we can have just improving R2 which is already a work in progress. I'm working on that just right now, as I told you. I'm working on doing it, a native R2 plugin, and introducing some improvements to that. Also, I would really like to implement an open source solution for that approach presented by the QSynth paper for synthesis of sub-expressions and further reconstruction of the original obfuscated expression. And also, it makes sense to detect patterns and to somehow memorize synthesized tasks to not repeat them. So somehow have an offline database of already synthesized tasks that we can reuse them for free. Because usually some operators appear many times as different obfuscation transformation. So that would make a lot of sense as well, to have some offline memorized component to reuse those for free. For references, here you have a few of them. First of all, chapter 5 on obfuscation of the Practical Reverse Engineering book. Also, the tutorial on software obfuscation, which is a quite long document by Banescu et al., which is the one where we extracted the table I showed you before on obfuscation techniques. Then the book of surreptitious software by Christian Colbert, which is also the creator and I guess maintainer as well of the Tigres obfuscator. Then there is a recently uploaded course on GitHub about advanced binary deobfuscation, which is quite interesting and really useful. If you are a little bit more hard into theoretical aspects, dealing with mixed Boolean arithmetic, and so more from a theoretical standpoint, as I said, you need to read the PhD thesis by Ninon Ayrols, the obfuscation with mixed Boolean arithmetic expressions, reconstruction, analysis, and simplification tools. Then also, if you're interested in the program synthesis approaches I described, you certainly need to take a look at the paper on Cynthia, synthesizing the semantics of obfuscated code by Tim Blasetko and others. And you also have a couple talks on CCC and Black Hat from 2017 and 2018, where they present their research and they gave also some examples with that. And the other paper of Cuisine that you have here, it's also really interesting, where they present all their work on the offline enumerative program synthesis approach for code deobfuscation, and they introduced that idea of synthesizing sub-expressions and reconstructing the original deobfuscated expression afterwards. So that will be all. Thank you for your attention. If you have any question, any comment, anything, you can always reach me on Twitter, as you have here, and also in that mail address. That would be it, and hope you enjoyed it. Thank you very much.